right, folks, it's on now. We're going to do some examples, just 3 problems from your problem set that you have today. Section 3.3, day 2, using congruent triangles. So you're definitely going to use Cpctc. You're also going to use this new definition that was in the last lesson called a definition of a line perpendicular to a plane, right? A line perpendicular plane. So lines can be parallel to planes, lines can intersect planes, or they can specifically be perpendicular to planes. And that allows us to conclude things, right? Not just that it's hidden at 90-degree angles. Well, what is an angle? Angles are made out of rays, and angles are made out of lines. But anyways, line perpendicular to a plane, that means that that line perpendicular to a plane is perpendicular to any line that's on that plane. That's how that one's defined, and we're going to use that here in number 4, also number 17. Not going to come up in number 18, but those are the 3 examples I'm doing today. Okay, so just a quick reminder, what you have up here, this is your whole problem set. So you have 11 problems. The last 2 problems are super quick because they're just from the self-test, but the other problems take some time, right? Might take about 5 minutes each or so. So there are 7 problems that take kind of a long time, about 5 minutes each or so, and then 2 problems should take you like 30 seconds to do the last 2. So thinking about 35, 40 minutes of thoughtful homework. Got to focus, again, harness that brain energy and get the work done, and you can be fine here. All right, so let's check out number 4 here. It says given. Okay, do number 4 along with me. You might want to re-sketch out the diagram too, right? So as I'm going to mark up this diagram, I think that's helpful. Anyways, given M is the midpoint of segment AB. Okay, so I'm not even reading the problem. I'm like, just as soon as I find something that I can gather intelligence on and add to the situation, that's going to make it easier for me to diagnose what I need to do and actually like go ahead and solve what it is we're looking for at the end. So, but the first given premise is that we're given that M is the midpoint of segment AB. So I'm going to do this. I'm going to check mark there, just to remind me that that line segment and that line segment, they're going to be congruent because that'd be congruent by definition of midpoint. Okay, plane X is perpendicular to segment AB, okay, segment AB. So here's segment AB here. Here's plane X right here. So what it's using here is that, right, AB is a line, X is a plane, okay? So we're going to use in this one, this new definition they gave us in this section, sort of randomly, definition of a line perpendicular to a plane. Okay, line perpendicular plane. We're going to use that to maybe say something about another line in this diagram here, okay? So we're given that here. We got to know what that definition is here. We got to use it. That's why that was on your exit ticket yesterday, right? What are some things we can immediately conclude based on the definition of a line perpendicular to a plane in maybe this situation or any situation we have here? Okay, what can you deduce about the figure? So step 1, what I can deduce about the figure, explain your plan for proving that your conclusion is correct. I can deduce several things. My guess is that you guys are just going to put together a list of things you can produce. I mean, number 1, I can deduce that AM equals MB, and that's through definition of midpoint. So here they don't really give you a proof. They're just like saying, what can you deduce? So my guess is that they want you to prove something like interesting, something kind of complex. So that's really not that interesting. It's probably more that we can say here. So there's really no end game with something like this. You're just saying, what can you deduce? And we can deduce that AM equals MB. I marked that up. We can also deduce that from this given premise here, plane X is perpendicular to segment AB. We can deduce that AM is perpendicular to not just plane X, but is perpendicular to MP, segment MP, okay? Because MP is on plane X. MP is a part of plane X, is contained by plane X. So that means that the line perpendicular to the plane is perpendicular to any line on that plane that intersects the line itself here, okay? So what that is, the reason for that is definition of a line and plane that are perpendicular to one another, okay? Definition of a line perpendicular to a plane, or definition of a line and a plane that are perpendicular to one another. That's that, right? A line is perpendicular to another line because that line is on the plane that other line is perpendicular to, and they intersect each other. So it's really, really wordy. That's why I want to spend time on it to kind of get it, but that's it here. There's actually no mention of the plane itself and what gets established here, because if we have this plane, right, if we have this plane X and it's perpendicular to that line, then hey, a line on that plane got to be perpendicular to that line as long as it intersects it here. Okay, so we have that. That's perpendicular. So what we can also say is this. I can maybe deduce this here, that these are more than just perpendicular. These would be congruent to one another. So maybe I'll do that as my third reason here, that angle AMP is congruent to angle BMP. Reason for that? Well, we knew that they were perpendicular, right? This is perpendicular right here, right? So they form 90-degree angles, and that's all good. But we have that crazy theorem that we use every so often, which is that adjacent angles formed by perpendicular lines are congruent to one another. So interesting here. It looks like maybe we might be able to get to just more than angles being congruent, these two segments being congruent. I think now that I have a segment, now that I have an angle, maybe what this problem is, we can prove a couple triangles are congruent to one another. What are the triangles that are going to be congruent here? Well, I can also say that MP is congruent to itself. MP is congruent to MP, and the reason for that, any shape is congruent to itself by reason of the reflexive property. Okay, so I can say MP is equal to MP, distance MP equals distance MP, and that is reflexive property of equality. So now I think ultimately the thing that the problem was kind of getting, I think where your brain probably went to is like, what's this getting at here? Oh, you can prove triangles are congruent to one another. You can through this here. So what do we have here? We have two sides that are congruent, an angle that's congruent to another angle, and then we have another pair of sides here. This is a shared side between the two triangles. So by the reflexive property, you got to use that. You got to flex the reflexive property to actually say that, because now we have an SAS correspondence, that I've kind of already addressed and kind of talked about here. So now I can finally conclude that triangle AMP is congruent to A corresponds to B, so I gotta go to B down here, triangle B, and M corresponds to M here, BMP as my answer here, okay? And reason for that would be SAS. Okay, so I think kind of what this question is getting at here is, what can you deduce about the figure? Okay, they don't really say with the figure, right? Because they show a plane in the figure. They show this larger triangle right here. You can deduce that it's isosceles. Oh, interesting. You might say that. I might do that. I might say that the figure is isosceles. This figure right here is isosceles. I might get to that. But you also might say that the two triangles are congruent here through SAS. So I might actually keep building on this on here. It's just so you see what I'm saying. Like, what are we talking about isosceles right now? Check it out. We have a congruent triangle right here. We have another congruent triangle right here. And we have another triangle here on the outside. So I might highlight yet another color. I'm gonna do this in pink. Check out this triangle here. We can actually say something about this triangle on the outside. This is a special kind of triangle right here. Well, it's definitely not equilateral because that side's like way longer than the other ones here. But I know that, hey, this top triangle is congruent to this bottom triangle. PMB is congruent to PMA, triangle PMA. So if those two triangles are congruent through Cpctc, those corresponding sides of the congruent triangles are congruent to each other right there through Cpctc. So we know that step 6, we could say, if we're just trying to prove whatever we can prove by this diagram here, we could say that we know that AP equals AP, and that's through Cpctc. And here, right, what we can actually prove, another interesting thing about this diagram here is that if you have a congruent triangle on top, a congruent triangle on the bottom, and they share that side in between, it's going to form an isosceles triangle. It's going to form an isosceles triangle. So what we can say here is our final step of another thing that we can prove about this diagram here, that triangle APB is isosceles. So that's interesting that we can get to that here. And that would just be their definition of isosceles triangle. Remember, an isosceles triangle is a triangle where at least two of the sides are congruent. We got that up here. We got that these two sides were congruent to one another. Sorry, AP and PB. I meant to put PB right here through Cpctc. And there we have it. Okie dokie, so let's keep running with it. You guys got more proofs to do, stuff to get down, so you're drawing this diagram out. It doesn't have to be a perfect diagram. It's hard to draw diagrams in 3 dimensions. I know that this diagram is a 3-dimensional drawing, so it's going to have some depth to it here, and then we have a plane that's being cut, I guess, like multi-planar kind of diagram here, right? So we have kind of the triangles coming above and below. Like if this is the plane where plane X is that goes on forever, the triangles slicing in here, and I'm guessing that they're perpendicular, right? Because this had to do with lines being perpendicular to planes, and probably have to do that here. So let's check this one out here. We'll mark stuff up to PA and QP, right? So segments PA and segments QB aren't perpendicular to each other. They don't intersect at all, actually. They're perpendicular to plane X. Perpendicular to planes. So here we have some lines perpendicular to planes. So what are we going to say? We're going to say PA is perpendicular to plane X, right? That's a given. But we can also say that PA is perpendicular to segment AB. And that would be through the definition of a line perpendicular to a plane, because a line perpendicular to a plane is a line that when it intersects the plane, any line that's on that plane, and AB is on plane X, okay, any line on that's contained in the plane that intersects that line that's perpendicular to the plane, that line is also going to be perpendicular to that line, right? So it's a really, really wordy one, but we're going to use this to say probably that PA is perpendicular to AB. Segment PA is perpendicular to segment AB. Okay, and then we're also probably going to say segment AB is perpendicular to segment QB, because it's given to us that segment QB is also perpendicular to plane X here. O is the midpoint of segment AB. Okay, so let's check this out here. O is the midpoint of segment AB. So I'm going to do a little tick mark there, and we're going to try to figure out, is O the midpoint of PQ? Let's check it out here. Well, if I can get those two triangles congruent, right, shouldn't I be able to say this? That those sides are congruent to one another? I put a little question marks here. I do that when I'm trying to prove this, and it's not given to me. I haven't proved it yet. If I am able to say that that side of that triangle and that side of that triangle, they're corresponding parts, but are they congruent, right? Well, if we knew that this triangle is congruent to that triangle, then we'd be good to go. And what else do you see here? What else can you mark up on this diagram here? There are two things that I like to mark up when I see diagrams right away. One is the reflexive property. If triangles share a side in common. So like on this one here, I would just look at this and I should just mark this up because that side is reflexive here. There's nothing reflexive here. This triangle doesn't have anything overlapping really, like not an overlapping side at least, or an overlapping entire angle. There's a vertex that share, but the angles aren't overlapping. So we're not going to use the reflexive property here, but what are we going to use? Well, we share a vertex here. So these are vertical angles. There we go. So we got to say this at some point. And then I think I see it. Do you see it? If you're perpendicular, then, right, you're going to measure 90 degrees, you're going to measure 90 degrees. Those are going to be congruent too. So here we're going to have an ASA correspondence and an ASA correspondence here. So these triangles will be congruent by ASA. Anyways, there's a lot going on with this one. I'm expecting this one to be pretty hard for you guys here. So let's see if we can just give this one a shot and clean it up, maybe get some ideas. So I always mark up the diagrams. I like to figure out kind of what's going on here. And that's what I recommend to you too, not just jumping in and writing the proof. Mark it up, think of some things you can say. And then, right, it's like you're doing an outline of an essay, thinking about an essay. And then you're going to start getting it down in the paper and you're going to refine from there, right? Refine from there, seek out help, get editing done, all that good stuff. So let's check it out here. But luckily, right, I compare writing a proof to like writing a paragraph, right? It's not like writing a full essay. So it's not quite that complicated, but it's like writing a paragraph here, perpendicular to plane X. So start with your givens. Okay, right, introduce the problem, start with your givens here to plane X. That's a given premise. We have a second given premise, which is that O is the midpoint of AB. And we got to think game plan now, okay? So I want to get, thinking backwards here, I want to get O is the midpoint of PQ. So we got to think about like how I can prove that. How can I prove that O is the midpoint of PQ? Well, if I knew that those two segments were congruent, good to go, right? O would meet the definition of midpoint here of segment PQ. So if I get those two triangles congruent, we're good to go. And I think I've already marked it up. I'm gonna get them congruent by ASA. I just need to figure out what I need to say now, how I can start with my givens and then move towards ASA. First thing I can do to move towards ASA is that I wanna get these angles congruent to one another. Angle A and angle B here, get them congruent to one another. And the way I'm gonna do that is, well, we're given that we have lines perpendicular to a plane, okay? Perpendicular to a plane. So we're allowed to say that PA is perpendicular to segment AB, okay? And that is, from this given premise, so it was perpendicular to the plane, so it's perpendicular to that line that's on the plane that it intersects. So that's the definition of a line and a plane that are perpendicular, okay? So that's going to get us to this. It's also going to get us to that, what do we have here? QB, yeah, QB is perpendicular to AB. And one thing that I'm noticing now that I didn't consider earlier too, is that these two lines are each perpendicular to the same line, So they're parallel to one another. Yeah, they're parallel to one another. So that means that you could prove these are congruent because they're alternate interior angles cut by two parallel lines and a transversal. So that might be the direction that I take this, because I think that might be easier than proving that those two angles are the same. Or maybe I'm not going to deal with parallel lines. No, let's not deal with parallel lines. Not just do it a different way. Anyways, okie dokie. The whole goal is we want to get those two angles congruent to one another. So the fact that they're both perpendicular, I'm actually going to stick with definition of perpendicular and definition of right angle to get us there. Because what I think we just let's not deal with the fact that those would actually be parallel, right? These are alternate interior angles that are congruent. These would be parallel. But anyways, let's just try to say that these measure 90 somehow. So whatever. So in order to get them to measure 90, first of all, definition of perpendicular are two lines that form what? They form right angles. And then right angles measure what? They measure 90 degrees. So here's how you're seeing your book do this. They're doing this. Measure of angle A equals 90, which equals measure of angle B. This is how they've been, in their fill in the blank proofs, been like making this process a little bit faster here, okay? Because remember, perpendicular lines get you to right angles, right? Perpendicular lines are two lines that intersect to form right angles. Well, that doesn't tell us that they're equal to each other. They just said they're both right angles. So if they're both right angles, they would both measure 90 by the definition of a right angle. And if they both measure 90, then they would equal each other, okay, through the transitivity property. So the thing that your book's been writing down, if you want to do it this way, they've just been writing down definition of perpendicular and definition of right angle. So you can use that too. I don't want to spend more time on this, but feel free to ask me questions about that if you have that there. But remember, just perpendicular lines, they make right angles. Right angles make they're 90-degree angles, so they must be equal to each other. Okay, so they don't put transitivity down there too. They just put definition of perpendicular gets us the right angles, and then we don't even say anything about right angles. We just say they both equal 90, they both equal each other. So you feel free to use that in the future to save you time. Okie dokie. So here we got a pair of angles of these two triangles congruent to one another. Okay. Right, we got a pair of angles. We got our A here. We got our A here. We just need to do ASA. So maybe let's do these angles right here, the vertical angles. I like using that earlier in proofs rather than later in proofs. So I'm going to say angle POA is congruent to angle QOB. And the reason for that is vertical angles are congruent. And finally, okay, so that's a set of angles. Here's a set of angles. And finally, we need to get the included side. So in order to use ASA, it needs to be A followed by the included side, followed by the non-included angle there that includes the side, or whatever. So we got the A's already. We said the A's, right? The vertical angle is taken care of. We haven't said why we know that AO equals OB. And the reason is this, right? O is the midpoint of segment AB. So through definition of midpoint, building on this from step one, the given O is the midpoint of segment AB, then that means we can apply the definition of a midpoint to say that AO equals OB. And that's definition of midpoint. There we have it. So we got angles, and finally we have included sides. I should have put the included thing here. We have included sides, right? It's included because the angles like share this side as a part, right? The sides in between those two angles, basically. And that's going to be enough for ASA to prove that the two triangles are congruent. So here we go. So then we have it. We have triangle PAO congruent to triangle QBO. And that is through ASA. And what is it we're trying to prove here? We're trying to prove that O is the midpoint of PQ. Okay, so last steps are going to be, we have the two triangles congruent. We need to get O as the midpoint. So through Cpctc, I can say that OP equals OQ. That's through Cpctc. And then here, there we go. We got the midpoint. That's the midpoint of PQ. If PO equals QO, we got it here. So we got PO equals QO. So we got O is the midpoint of PQ. And that is from definition of midpoint. So this is an 8-step proof for you. Oh man, that's kind of a lot. That's kind of a lot. Hopefully the other ones are a bit shorter that you have there. Okay. Email if you have questions on that one. I'm going to do this one in a second. I'm just going to pause this video for a second, but I'll do this one in a second. All right, and last one. We're back on it here. Okay, so now we got this one here. We're actually not given a diagram, so we darn well have to draw it, even though we have to draw it again too to mark it up and make your life a little easier. Yeah, it was a little bit complicated one. Hopefully that one made sense. Anyways, we got to draw the diagram, and because we're going to use that, we're going to prove something about it, which is pretty exciting here. So first, draw the figure and state what's given and what is to be proved. Then write the proof in two-column form. So again, what are we doing this class this year? Why is this important? We want to prove facts, right? We want to prove facts, and facts aren't oftentimes laid out for you, having a diagram, having exactly like this is how to word the fact. Facts are things that you think about and think like, I think I can prove this. I think I can do this here. So this is sort of presented this way. It says that PQ and PR are the congruent sides of isosceles triangle PQR. The bisector of angle P meets segment QR at K. Prove segment PK is perpendicular to segment QR. Wow, that's a lot to digest. I imagine some people reading that being like, I don't know where to begin. So maybe let's just try to chunk this up real quick because I think this feels overwhelming. First of all, we're going to know that PQ and PR are congruent sides of isosceles triangle PQR. So maybe let's just try to write this down in a way that we usually see on proofs. So given, okay, if we're given that PQ is congruent to PR, okay, that's going to be something that's going to be given to us here. Of isosceles triangle PQR, okay, so then we're going to have triangle PQR somewhere is given to us. I don't really need to write that down, but I'm writing it down just to store it here. We have a triangle PQR. The bisector of angle P, okay, so bisector of angle P meets QR at K. So it sounds like that the bisector of angle P, because it meets QR at K, that ray PK is the bisector of angle P, here. And I don't know how else to best describe it here. Well, anyways, let's just check it out. I think we need to start with an isosceles triangle. I think that's like the first thing to really think that we need to do. So let's go ahead and draw that. And this is why grid paper comes important, just because it makes drawing isosceles triangles easier. I think it's got a slope to draw an isosceles triangle. So I want to go over 1, 2, 3, and go down 1, 2, 3, 4, 5. And that can be one of the two congruent sides. And then I'm going to go over 3, 1, 2, 3, and go down 5, and boom. And here is an isosceles triangle, okay? That's drawn right, pretty close to isosceles. I try not to draw it equilateral, and it's not. This side's a little bit smaller. Let me redraw that, actually, just because it looks kind of equilateral. I want to avoid special cases like equilateral triangles. Okay, so I'm going to go down 5 and over 2 instead. Okay, there we go here. And here, this is maybe down here. Okay, so this is a little better, I think. I think this is a little bit better for our purposes here. Okay, so anyways, PQ is one of the congruent sides, and PR is the other congruent side. So this is why this is isosceles. We have an isosceles triangle right in front of us here. Okay, and then we're going to be given a bisector. We know we're going to have a bisector. That's right here. We're going to have PK because this is side QR is down here. Good, we have a side QR here. A bisector of angle P, which like would hit the intersection right here. Okay. Right here, the bisector of angle P meets at point Q on segment QR. Okay, so here is part of the challenge of this is just drawing the diagram. So if you've done all that, pat yourself on the back. You feel pretty good because you've gotten set up this problem. What do we notice about this one here? Well, let's see. What's given to us is that this is an angle bisector, so I might just highlight this up like that, right? It's an angle bisector, so it's given to us here. Interestingly enough, this is interesting about isosceles triangles. This is a pretty important thing to know in the future when we study isosceles triangles we're about to go into now, that the angle bisector of, this is called the vertex angle, the top angle, right? The one that's where the congruent sides meet. It's called the vertex angle. The angle bisector of it is actually going to hit the third side, the base side of the isosceles triangle. It's going to hit it at its midpoint. Interesting, at its midpoint. So you could actually prove this. You can prove that these two sides would be congruent, and you can also prove that it's perpendicular as well, okay? We don't have to prove the fact that it's the midpoints of the side QR, but we do have to prove that PK is perpendicular to QR, so that the angle bisector of the vertex angle of an isosceles triangle is perpendicular to its base at its midpoint, which is something that you're going to learn later, but the perpendicular base we're going to prove now. Okay, so anyways, let's just go ahead and do it. We're given this. That's what we're given. What we got to prove is that the foot of this, right, so where this is going to meet down here is going to be perpendicular, right, perpendicular to the base of this triangle, right? These are called the legs of an isosceles triangle. That's called the base. We'll get into that perhaps next class here. Okie dokie. So we're going to prove that PK is perpendicular to QR, and let's do that now. All right. Statements, reasons. Statement 1, PQ, congruent to PR. That's given. Another given is we're going to use that that we have a bisector. So ray PQ is the bisector of angle P. Okay, that's given. So how are we going to prove this? How are we going to prove that these are perpendicular? It makes it perpendicular on there. Well, look, we have two triangles right here. We have triangle PKQ and triangle PKR. And it can be proven that they're congruent to one another. Yes, it can. Yes, 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 yes. It totally can. So with this, okay, it can be congruent. And what we do here, how we would do this, well, this is an isosceles triangle, so we know that that side's congruent to that side. Through definition of angle bisector, we know those two angles are congruent. And then wait a second, what's something this triangle and that triangle have in common? They're overlapping in some way. They both share PQ, okay? They both share PQ. So PQ is congruent to PQ by what reason? Okay, you got to use that, right? You got to use that. Yes, 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 yes. It's the reflexive property, right? The reflexive property. So I'm going to mark that congruent to itself. So here is how I'm going to do this. I'm going to get an SAS correspondence and an SAS correspondence. That means the two triangles are going to be congruent by SAS. And then I'm going to know that those two angles down here are congruent by Cpctc. And then I have adjacent angles, two lines that form congruent adjacent angles must be perpendicular to one another. That's the last thing I'm going to use. Man, there's so many reasons. There's so many reasons in geometry. You with me? I don't know. Let's just do it together. Let's get through it together. Okay. Anyways, we are trying to get triangles congruent. So here we have a pair of sides that are congruent. Let's get the angles next. That was how we're going to build on this with the PQ thing. Okay. So sorry, the PK thing. PK thing is going to, the fact that it's a bisector is going to mean that angle QPK is congruent to angle RPK. Because of definition of angle bisector. All right, and that's going to tell us a pair of angles are congruent. And that's great because we're trying to get two triangles congruent first so that we can then say these two angles are congruent. And therefore, they'd have to be perpendicular too, because if two lines intersect and they form congruent adjacent angles, then the lines are perpendicular. Ooh, man, that some of these theorems we learned in chapter 1, they just come back. They come back to you here. Okay, the way we're going to get there is through SAS, because again, we have a side, we have an angle, and we can prove that that side is congruent to that side, that angle, and this side, because they're the same, right? They're the same. You're not going to just say they're the same in a proof. You have to say the reflexive property. You got to know the reasons here too. You got to know your reasoning down here, the accepted reasoning. So PK. Segment PK is congruent to segments PK. And this is why I spent a lot of time on this on the exit tick the other day, is because the reflexive property as a reason is something you're going to use a lot in proving two triangles congruence, because oftentimes they will share a side or share an angle that appears in both triangles. All right, there we go. So now we have sides, we have angles, and we have sides. So we can use the SSS triangle congruency shortcut to say that triangle QPK is congruent to triangle RPK, and that is by side, angle, side postulate right there. We're good to go. Step 5. Okay, step 5. What do we got for step 5 here? That angle QKP congruent to angle RKP. And that is by Cpctc. Remember, Cpctc always appears after SAS, SSS, ASA. It always appears once you have congruent triangles, then you can say their corresponding parts are congruent. Okay, so corresponding parts of congruent triangles are congruent to one another. And yeah, that gets us this. And this is what I'm trying to talk about earlier to try to show you is that if we knew that line PK and QR, they intersected and they formed adjacent angles that are congruent, because we've done that through Cpctc, then we would know that the two lines had to be perpendicular. There's only one way that two lines can intersect one another and create two adjacent angles that are congruent, is because they both have to measure 90 degrees, because they both measure the same. They both add up to 180 because they would be supplementary to one another. So anyways, we have that theorem that tells us that to allow us to finish this, I can get it done in six steps. Your steps might be longer if you figure out this theorem, that PK is perpendicular to QR, because if two lines, so two intersecting lines, I have this written, if two intersecting lines form congruent adjacent angles, then the lines are perpendicular. And we're good to go. So tons of proofs on this one. Man, at least I did 2 of them for you. So as long as you get through 6 or so, you're fine. Like, it's kind of a lot, but it is what it is. And yeah, you got to flex that mental strength you have, right? Because we're good here, right? We're good at our stuff. I'm good at what we do. And hopefully you find yourself getting better. All right, email me if you have any questions. Good luck on all this. See you guys later. Bye.